Think about your organization's external footprint for a second. If a motivated threat actor spent just 30 minutes mapping your domain right now without sending a single packet to your firewall, what forgotten subdomains, exposed environment files, or dangling cloud credentials would they find?
Yeah, that is it's a genuinely sobering thought because, the reality isn't a hypothetical. They are looking right now. I mean, if you look at the logs, the probes just hit constantly.
Right, and looking at the research today, the sheer velocity at which this happens is just, it's staggering. We really need to talk about that recent incident that completely blew my mind, the LM deploy SSRF vulnerability.
Oh yeah, CVE 2026 33626.
Exactly. For those tracking the specific identifiers, an AI inference infrastructure was weaponized in just 13 hours. 13 hours after the public advisory went out.
Yeah, 13 hours is, I mean, let's be real, that's barely enough time for a security team to even parse the advisory, let alone, test it in staging, get change management approval, and deploy a patch across a production environment.
Right. It's impossible.
It is. My heart really goes out to the SOC analysts on the ground when things move that fast. You're literally in the trenches fighting the clock. It just feels impossible.
It does. And what struck me wasn't just the speed, but the precision of it all. The attacker didn't just stumble around in the dark, throwing payloads at the wall. The post-mortem analysis shows they executed this incredibly methodical 8-minute, 10-request reconnaissance campaign.
8 minutes.
8 minutes. They targeted AWS IAM credential endpoints, specifically that infamous 169.254.169.254 metadata service and internal Redis and MySQL services. And they did all of this via multimodal AI image loading.
That is just terrifyingly precise. It shows they didn't just want to see if a server-side request forgery payload worked. They arrived with a highly specific operational objective.
Right, they knew what they wanted.
Exactly. They knew exactly where the high-value targets were located within that cloud architecture before they even fired the exploit. They had already done the math.
So today, we are taking a massive deep dive through the modern attack lifecycle to understand exactly how this happens. We're going to break down how attackers see your infrastructure using passive OSINT and Google dorking, how they transition into active enumeration, the deep mechanics of exploiting web apps and cloud IAM, and finally, how defenders are actually using WEFs, RSPB, the ELK stack, and the NIST incident handling framework to catch and contain them. We're getting deeply technical today, so buckle up.
I am so ready for this. The mechanics of these attacks are, they're fascinating once you pull back the curtain. Let's unpack the whole life cycle.
Okay, let's start at the very beginning of the MITRE ATT&CK framework, Tactic TA00043, reconnaissance. Building off that LM deploy attacker's rapid recon, I want to explore how attackers figure out what to target in the first place without triggering a single SIEM alert. Because, as defenders, we rely on logs. If there are no logs, we are completely blind.
That's the critical distinction we have to define right up front, I think. Passive versus active reconnaissance. When we talk about passive reconnaissance, it means absolute zero packets hit the target servers. None.
Not a single one.
Right. You aren't touching their load balancers. You aren't hitting their DNS servers. Nothing. You are relying entirely on third-party repositories, search engine indexes, public registries, and historical data sets. You leave absolutely no digital footprint on their infrastructure.
I always think of it like casing a bank by going down to the city planner's office and looking at the public architectural blueprints. You never actually set foot on the bank's property. You don't walk past a single security camera, but you still know exactly where the vault is and where the air ducts run.
That is a perfect analogy. You are gathering the blueprints from the public record. And arguably, the most powerful place to look at those blueprints today is certificate transparency logs, or CT logs.
Oh, yeah.
Every publicly trusted SSL or TLS certificate issued by a certificate authority is logged here. It's a cryptographically verifiable, auditable public record.
But wait, let's dig into the paradox of that for a second. CT logs were created to secure the web, right? To prevent rogue certificate authorities from issuing fraudulent certs in secret. But by making it public, we've essentially created a massive, searchable map of every server on the internet. Tools like crt.sh let anyone search these logs for a root domain in seconds.
Exactly the paradox. The security mechanism itself becomes the reconnaissance vector. I mean, let's say your DevOps team spins up a temporary staging environment. They call it something obscure like apstaging-v2-migration.yourcompany.com.
Right, something super long.
Yeah, they want to test it over HTTPS, so they use an automated ACME client to grab a quick Let's Encrypt certificate. The second that certificate authority issues the cert, it is broadcast to the CT log network. that subdomain is now permanently recorded.
Oh, wow.
An attacker querying those logs instantly knows that staging environment exists, even if you never link to it anywhere on the public web, and even if it's protected by a firewall. The name is completely burned.
So even if it's an internal-only subdomain, if it gets a public cert just for convenience, the secret is out forever.
Precisely. And the logs are append only. You cannot delete a CT log entry. Once it's there, it's there. Attackers pull these logs, compile lists of thousands of subdomains, and then they combine that with historical DNS intelligence.
Okay, let's talk about the DNS intelligence, because we hear about WHOIS and RDAP all the time, but the research highlights passive DNS tools, specifically mentioning netlist.io. How does a tool like Netlist compare to something like Shodan? I feel like Shodan gets all the spotlight when we talk about attack surface discovery.
Shodan definitely gets the spotlight, and I mean, it's brilliant for what it does, scanning the entire IPv4 space for open ports, banner grabbing, and device fingerprinting. If you want to find an exposed webcam or an unpatched Exchange server by its banner, Shodan is your tool. But Shodan is a point-in-time snapshot of the active internet. Passive DNS services like Netlist or Security Trails, they let you see the history of a domain.
The history, like what it used to resolve to.
Exactly. Netlist has these massive data stores and APIs that track historical IP resolutions, and this is a huge blind spot for a lot of organizations. Let's say you had a direct-to-origin web server at IP address 203.113.50. You get hit by a DDoS attack, so you scramble and put a web application firewall or a cloud proxy like Cloudflare in front of it.
Makes sense.
You change your DNS hour record, so www.yourcompany.com now points to the WF's IP.
Right, so now all the traffic goes through the security filter.
In theory. But the origin server at that original 203 IP is still sitting there on the internet. Netlist remembers that historical DNS record. An attacker queries Netlist, sees the old IP address, and simply bypasses your shiny new WAF by sending HTTP requests directly to the origin IP.
No way.
Yeah. If you didn't configure your origin firewall to explicitly drop traffic that doesn't originate from the WAF's IP ranges, you are completely exposed.
Wow. You think you're protected because you changed the DNS, but the internet just never forgets. That is wild. But here's where it gets really interesting, I think. Google dorking. Using Google's advanced search operators for open source intelligence. Now, I know developers accidentally expose .env files all the time, but how is Google actually indexing them? If a web server is configured properly, or if there's a robots.txt or a reverse proxy, how does this stuff leak into a search engine?
That is the billion-dollar question.
No.
Google's crawler, Googlebot, is incredibly aggressive. It indexes like 8.5 billion pages a day. It doesn't care if you meant to publish a page.
It just scrapes everything.
Everything. The leaks usually happen due to misconfigurations in the web root or CI/CD pipelines. For example, a developer might copy a project folder to the production server, and the web server, say Nginx, isn't explicitly configured to deny access to hidden files starting with a dot, like .env or .git. Or someone creates a backup file like config.php.bake.
Ah, I've seen that.
Right. The server knows how to execute .php files, but it treats .back as a plain text file. So when Googlebot stumbles across a link to it, perhaps from an open directory listing, it just reads the source code and indexes the database passwords right in plain text.
So the attacker doesn't even have to scan your server. They just ask Google what it found. The research breaks this down into 5 critical operator families. Let's dig into the mechanics of these, because it's not just typing keywords, it's programmatic searching.
Right. It's highly structured. The first family is scooping. The foundation is site.targetdomain.com to restrict results. But the attacker doesn't care about your marketing page. They want the shadows. So they use site.targetdomain.com-www.
Okay, so a minus sign?
Yeah, that minus sign is a Boolean not T. It strips out the main website that everyone knows about, filters the noise, and leaves you looking exclusively at the forgotten infrastructure, the dev portals, the weird subdomains Google somehow found a path to.
So turning off the spotlight so you can see what's hiding in the corners.
Exactly. Then you move to the second family, file and content operators. This is targeting those misconfigurations we just talked about. You search filetype.env combined with the text dbpassword. If you run that query right now, you will find live database credentials for companies all over the world.
That's terrifying.
It collapses a multi-stage intrusion, finding a vulnerability, getting a shell, escalating privileges, reading files into a single Google query. Another classic is entitled Index of.
Right. That targets Apache or Nginx servers where directory listing is accidentally enabled. So if there's no index.html file, the server just generously lists out all the files in the directory like a file explorer.
And you'd be amazed what gets left in those directories. Database dumps, log files, zipped source code. Which brings us to the third family authentication surface. Before an attacker tries to break in, they want to map out all the doors. They use interal.login or entitled.vpn. They're looking for the legacy remote access portals that maybe haven't been integrated into the company's single sign-on provider and therefore probably lack multi-factor authentication.
Finding the obscure doors, and I imagine they need to know what kind of lock is on the door, which leads to the fourth family.
Yes, technology fingerprinting. You can't just blindly throw WordPress exploits at a React site. You need to know the stack. Attackers will search entitle.chpinfo to find exposed PHP configuration pages. A finfo page tells you exactly what server version, what operating system, and what modules are running.
Handing over the blueprint.
Literally. Or they look for unauthenticated monitoring stacks like entitle Grafana or entitle Elasticsearch. You find the exact version number from the Google snippet, cross-reference it with the CVE database, and you have a tailored exploit path.
And the final family is threat intel, which is looking outside the primary domain, right?
Yeah, this is about leveraging third-party breaches. Searching paste sites using site.paston.com, targetdomain.com to see if employees' credentials have been dumped from previous breaches. Or, more commonly now, site.github.com, target.com, token OR secret. Developers constantly accidentally commit AWS API keys or Slack tokens into public repositories. Google indexes it, and the attacker finds it.
Okay, I have to push back a little here and talk about the legalities, because this is a huge gray area for a lot of people. If I'm a security researcher or just a curious sysadmin, and I use a complex Google dork, and I stumble upon an exposed.env file with a company's database password, when does this actually cross the line into Computer Fraud and Abuse Act or CFAA violation territory? Am I breaking the law just by running the search?
It's a vital question, and the legal line is actually quite specific, though it can feel blurry. The Google query itself is perfectly legal. Google's crawler did the work of retrieving the content from the target server and indexing it on Google servers. When you run the dork, you are interacting with Google, not the target. Google is just returning search results based on public data.
So reading the password on Google search results page is technically fine.
Yes, but the line is crossed the moment you interact with the target system based on that information. Taking that database password and trying to log into their MySQL server, that is unauthorized access, CFAA violation.
Makes sense.
Taking that exposed API key and sending a request to their AWS environment, unauthorized access. Even downloading a database backup from that open directory you found via Google can be considered unauthorized access, because even though there was no password protecting it, the data wasn't intentionally made public for you to take. The practical technical test I always teach is this. If your activity generates server-side logs on the target's infrastructure, you have moved from passive recon to active interaction. And if you don't have authorization, you're in dangerous waters.
That makes total sense. The log file is the boundary. And obviously doing all this passive mapping manually sounds exhausting. Attackers aren't just sitting there typing dorks one by one.
Oh, absolutely not. It's heavily automated. But there's a catch. Google aggressively rate limits automated queries to stop scraping. If you just loop a Python script to run 500 dorks, Google will hit you with PCHAs or temporarily IP ban you after 10 or 20 searches.
So how do they get around it?
Attackers use specialized tools like Pagodo, which runs payloads from the Google hacking database, but uses randomized sleep delays and user agent rotation to mimic human behavior and avoid blocks. They also use tools like the Harvester, which acts as a meta search engine, pulling from Baidu, Bing, LinkedIn, and Shodan simultaneously. And the modern twist, we're seeing LLM-based dork generators.
Oh, of course. AI.
Right. An attacker doesn't even need to know the syntax anymore. They just type into a local LLM, find me exposed Jenkins servers belonging to this company that might have directory listing enabled, and the AI generates the perfect, complex Boolean search string.
AI really is accelerating the friction points at every phase. So let's look at the board. The attacker has mapped our external footprint completely passively. They have a massive list of subdomains from the CT logs. They've pulled historical IPs from Netlist to bypass our WA, and they've used Google dorking to find forgotten staging portals and maybe an exposed config file. The passive recon is done. They have the blueprints. Now, they have to start tapping the glass to see what breaks. How do they transition to active enumeration?
This is a massive shift in tactics. This is where they finally step onto the property. Active enumeration means direct interaction with the target's infrastructure. The goal now is to find the assets that aren't in the public CT logs, aren't in Google's index, but are actively resolving in the target's internal or external DNS.
So we are talking about actively generating traffic. How does active subdomain enumeration work under the hood?
It primarily relies on DNS brute forcing and virtual hosts, or VOSA fuzzing. With DNS brute forcing, you take a massive word list, sometimes millions of common subdomain names like AP, dev, staging, VPN, test1, and you aggressively query the target's DNS name servers to see if those records exist. But it's the VOST fuzzing that is really insidious.
I hear Voost fuzzing mentioned a lot in bug bounties, but mechanically, how does it actually expose hidden infrastructure?
Okay, so think about how web servers work. A single Nginx or Apache server sitting on a single IP address might host 50 different websites or applications using virtual hosting. The server relies on the HTTP host header to know which application you want to talk to. If you just open your browser and go to the IP address directly, the server doesn't get a specific host header, so it just serves a generic default page or a 403 forbidden.
Right, because it doesn't know which of the 50 sites you want.
Exactly. So what attackers do is they establish a TCP connection to that IP address, but in the HTTP request, they dynamically swap out the host header. They send a request saying host-internal-api.targetdomain.com. The web server receives it, says, oh, I recognize that host name in my internal config, and it routes the request to a hidden, unauthenticated internal application that isn't publicly listed in DNS anywhere. It's a prime way to find shadow IT that the networking team thought was completely hidden.
That is brilliant and terrifying. You're literally asking the server to reveal its secrets by guessing the secret knock. Okay, so what is the tooling breakdown for this active phase? The research lists quite a few. Let's talk mechanics.
The tooling ecosystem here is vast and highly optimized. A major player is Subfinder. It's written in Go, which is critical because Go handles concurrency incredibly well. Subfinder can query dozens of passive sources and active resolvers simultaneously without choking on threads. Then there's Amass, which is maintained by OWASP. Amass is heavier, it takes a hybrid approach, it does passive scraping, active DNS brute forcing, and it even connects to commercial APIs like WHOIS XML or security trails to map out the entire autonomous system, the ASN, of the target.
Wait, how do these tools handle wildcard DNS? Like, I've seen configurations where a company sets up a wildcard record so that literally anything -u-type.target.com resolves to the same exact IP address. Doesn't that just absolutely flood a brute forcing tool with false positives? The tool would think it found a million valid subdomains.
Yes, wildcard DNS is an absolute nightmare for attackers and penetration testers. It ruins your dataset. And that's exactly where tools like Purids and Mastins come into play. Mastins is this insanely high-performance DNS stub resolver that can handle millions of queries a second. Purids acts as a wrapper around Mastins, and its entire purpose is to solve the wildcard problem mathematically.
How does it do that? How does it know what's real and what's a wildcard?
It establishes a baseline. Before it starts brute forcing your word list, Purins generates a bunch of completely random gibberish subdomains like xkqjzw.target.com and queries them. It knows these shouldn't exist. If the server responds with an IP address anyway, Purins analyzes that response. It hashes the IP, the TTL, the HTTP response body if it's a web server, and it creates a fingerprint of what a fake wildcard response looks like.
Well, that's smart.
Yeah, then as it brute forces the real word list, any response that matches that wildcard fingerprint is automatically filtered out. You are left with only the true, unique subdomains.
That is so clever. It dynamically learns the server's lie and filters it out.
Exactly. And once they have a clean list, they use permutation tools like GoTator. GoTator takes the valid subdomains you found, say it found appy and prod, and it generates intelligent permutations based on naming conventions. It guesses appy prod, prod appy, appy v1, appy v2. It uses the target's own logic against them. And for raw brute forcing power, there's Sublist 3, a Python-based tool that integrates OSINT but has a specific appy B flag you can throw to enable its subbrute module to just hammer the DNS resolvers.
Okay, so through all this, the attacker now has a massive refined list of valid resolving subdomains and hidden VOST. What is the immediate next step? Because a DNS record just points to an IP. You don't know if anything is actually running there.
Right. You have thousands of IPs. You don't want to manually open a web browser for each one. So they move to probing. They use tools like HTTPX from Project Discovery or HTTP Probe. These tools take that massive list of domains and blast them with HTTP and HTTPS requests. They parse the responses to tell the attacker which of these IPs actually return a live HTTP 200 OK status. What server headers are they returning? What are the page titles? They are mapping the live attack surface.
And crucially, in modern architectures, they aren't just looking for HTML web pages, they are hunting for APIs.
Absolutely. The web is essentially just a front end for APIs now. Attackers are actively probing specific paths during this phase. They're appending swagger.json, apdocs, or openrp.json to every domain they find. If they find a Swagger file, it's game over for obscurity.
Because Swagger is the API documentation, right?
Yeah. Right. It tells the attacker exactly what endpoints exist, what HTTP methods they accept, get, post, PUT, and what parameters they require. They use specialized engines like KitterRunner for this. KitterRunner doesn't just guess random file names. It is an API-aware fuzzer. It consumes Swagger specifications and uses them to intelligently format requests, guessing API routes and parameters that a normal web fuzzer would completely miss.
And we have to talk about GraphQL here. The research explicitly highlights GraphQL as a massive target during this active enumeration phase.
GraphQL completely shifts the paradigm. With a traditional REST API, an attacker has to discover every individual endpoint. With GraphQL, there is usually only one endpoint, like GraphQL. The vulnerability lies in a feature called introspection. If developers accidentally leave the introspection query enabled in production, which happens constantly, an attacker can send a specific JSON payload asking the GraphQL server, hey, what are you capable of?
And the server just tells them.
It doesn't just tell them. It hands over the entire abstract syntax tree. It returns a massive JSON document detailing every single query type, every mutation, all the underlying data types, fields, and arguments. It effectively gives the attacker a complete interactive map of the backend database schema. They don't have to guess parameter names anymore. The API handed them the dictionary.
Okay, but hold on. I need to understand the defense side of this phase. We're talking about blasting DNS resolvers with millions of queries, hitting thousands of IPs with HTTPX, fuzzing APIs with KitterRunner. Wouldn't an enterprise firewall or an intrusion prevention system immediately recognize this volumetric noise and just ban the source IP? It seems so loud.
You would think so, and if an amateur runs these tools out of the box from a single IP, they will get blocked instantly. But sophisticated attackers are highly evasive. They distribute their scans, they use proxy networks or leverage cloud functions like AWS Lambda to distribute their traffic across thousands of ephemeral IP addresses. To your firewall, it doesn't look like one guy scanning you 10,000 times. It looks like 10,000 different people visiting your site once.
That makes it nearly impossible to block by IP reputation.
Exactly. They also utilize low and slow TCP connections. Instead of a full-blown aggressive port scan that trips the threshold of a web application firewall, they trickle requests in. They might send one HTTP request every few seconds, staying just below the algorithmic thresholds that trigger an alert in your CM. They slip right under the radar.
Okay, let's unpack where we are. The recon is done, the target is acquired, they've bypassed the initial perimeter noise filters using distributed low and slow techniques. They've mapped the APIs. Now, how do attackers actually exploit the vulnerabilities they just found? Because discovering a GraphQL endpoint is one thing, successfully hacking it is another. We're moving from discovery to exploitation.
This is where we map all those recon findings directly to the OWASP Top 10 framework. The recon dictates the exploit. For instance, if that KitterRunner scan or that GraphQL introspection mapped out a detailed API schema, the very first thing an attacker looks for is broken object level authorization, or BOLE. You might also hear it referred to as IDOR, insecure direct object reference.
Right, BOLE. So if I understand the mechanics, this is a logic flaw, not a technical injection. It's like if my user profile URL is a PV1's users 1001, and I intercept the request and simply change it to 1002, I see someone else's data.
That's the exact mechanism. And the reason APIs are so vulnerable to this is because APIs are designed to handle data programmatically, separating the data from the presentation layer. The API backend assumes the front-end application is handling the logic. If the backend code doesn't explicitly run a check saying, is the session token provided in this request explicitly authorized to view the data for user 1002, it just blindly trusts the request and dumps the data. Or, moving away from logic flaws, if the active crawler found dynamic input parameters, they are going to immediately fuzz them for SQL injection.
The classic apostrophe OR1 equals 1 dash dash. It never dies.
It never dies because it works. If the application concatenates user input directly into a database query instead of using prepared statements, the attacker can manipulate the syntax of the query itself. And looking at the research, we can see how these specific flaws, both sexually vulnerable components, play out at massive scale in real-world breach breakdowns. Take the Equifax breach.
Let's talk about Equifax, because that is the textbook example of OSB06 vulnerable and outdated components, isn't it?
It is. Equifax suffered a catastrophic breach because of an unpatched remote code execution vulnerability in Apache Struts, a third-party open-source framework they use for their web applications. What's crucial to understand about the mechanism here is how the exploit worked. It was a flaw in how Struts parsed HTTP headers, specifically the content type header. Attackers could inject object graph navigation language or OGNL expressions into that header.
Wait, what does that mean in plain English? OGNL injection.
It means the attacker could put code into a standard HTTP header, and the Apache Struts framework would evaluate and execute that code directly on the server operating system. A patch had been available for months, but Equifax had lost visibility into their own environment. They didn't know they were running the vulnerable version. The attackers threw the OGNL payload, got a reverse shell, and sat in the network completely undetected for months, exfiltrating data.
Unbelievable. And then you contrast that with the British Airways breach, which was a completely different vector. That wasn't a server-side vulnerability at all, was it?
No, British Airways was a masterclass in client-side exploitation. It was a match card attack. The attackers didn't attack the British Airways backend servers. Instead, they compromised a third-party cargo contractor's account that lacked multi-factor authentication. They used that access to get into the network and modify a single JavaScript file that was loaded onto the British Airways payment page.
So they injected malicious code into the browser's environment?
Exactly. It's a document object model, or DOM-based attack. They added maybe 20 lines of JavaScript. As customers legitimately typed their credit card info into their browsers, that malicious script silently hooked the input fields, copied the data, and exfiltrated it to an attacker-controlled drop server in the background. The British Airways backend servers never even saw the theft happen because the crime occurred entirely within the customer's local browser process.
That is so insidious. You can patch your servers all day long, but if the browser is compromised, you lose. And then there's TalkTalk. That one always fascinates me because it highlights the human element, the insider threat.
TalkTalk was a perfect storm, a nightmare scenario. They had a legacy, unpatched database infrastructure with the glaring known SQL injection vulnerability, but the compounding factor was that they had outsourced a portion of their customer support to a third-party provider. Rogue employees of that provider realized they could use their authorized support access to harvest tens of thousands of customer records. They downloaded them onto USB drives and sold them to scammers. So you have a technical exploit vector lying wide open, combined with an authorized insider threat exploiting the data access. It shows how fragile perimeter security is.
Okay, let's circle back to the incident we opened the deep dive with, the LM deploy SSRF server-side request forgery. I really want to dig into the mechanics of this because SSRF is devastating in the cloud. How does it actually work, and why is that specific IP address, 169.254.169.254, the holy grail for attackers?
SSRF is conceptually simple but practically devastating. It occurs when a web application takes a URL as user input and then fetches data from that URL on the back end, but it doesn't validate the destination. You are tricking the server into making an HTTP request on your behalf. In modern cloud environments like AWS, every single EC2 instance is configured by default to be able to query a local, non-readable link local IP address 169.254.169.254. This is the Instance Metadata Service, or IMDS.
And what exactly does the Instance Metadata Service do? Why does the server need to talk to it?
It allows the virtual machine to ask the cloud provider for information about itself. What is my host name? What subnet am I in? But here's the critical vulnerability. If that EC2 instance has an IAM, Identity and Access Management role attached to it, the metadata service will also hand out temporary, highly privileged AWS security credentials for that role.
Wow.
So here's the attack path. The attacker finds an application vulnerable to SSRF. Say it's a PDF generator that takes a URL to convert. The attacker inputs http.169.254.169.254 latest metadata security credentials role name. The backend server blindly reaches out to the metadata service, retrieves the JSON payload containing the access key, secret access key, and token, and then reflects that JSON right back to the attacker in the HTTP response.
The server acts as a confused deputy. It walks up to the cloud provider, asks for its own admin keys, and hands them straight back to the attacker. It's like a hotel guest tricking the front desk clerk into opening the hotel's master safe, because the clerk assumes any request coming from inside the lobby must be authorized.
That is exactly what happens. And if that IMM role is overprivileged, which it almost always is in poorly configured environments, the attacker now has the keys to the kingdom. They can access S3 buckets, spin up crypto mining instances, delete databases. This is the precise mechanism used in the infamous Capital One breach, which the analysis references regarding the 106 million credit card applications stolen and the subsequent $80 million OCC penalty. The attacker used SSRF to steal IAM keys, installed the AWS CLI on their own machine, loaded those keys, and just synced 700 private S3 buckets to their local drive.
The stakes are incredibly high. So how do modern application architectures attempt to stop this? Because if the application code is vulnerable, we need compensating controls. The research dives deep into WAF versus RASP. Let's break down the mechanical differences between the two.
Sure. Let's start with the WA, the Web Application Firewall. It sits at the perimeter of your network, usually at the CDN edge like Akamai or Cloudflare, or as a reverse proxy in front of your load balancers. Its job is to inspect incoming HTTP traffic before it ever reaches your application servers. It uses signature-based detection, looking for known bad patterns. It uses regex to spot SQL injection syntax, or it rate limits traffic to mitigate DDoS attacks. It's incredible for virtual patching.
Virtual patching, meaning fixing it without changing code.
Exactly. If a 0-day drops on a Friday night and you can't patch your Apache servers until Monday, you can deploy a wave rule in minutes to block the specific exploit payload. The traffic is dropped at the edge. It adds maybe 1 to 5 milliseconds of latency to the request.
Right, so it's the bouncer checking IDs at the club door. If you're on the blacklist, you don't get in. But the research points out that the way lacks context. What does that mean technically?
It means the way only sees the raw HTTP string. It does not know how the backend application is actually going to parse or execute that string. Attackers know this, so they use encoding tricks, URL encoding, hex encoding, Unicode obfuscation, to disguise the payload. The payload looks like gibberish to the Wave's regex engine, so it lets it through. But when it hits the backend database, the database parses it, decodes it, and executes the SQL injection. The way is blind to the execution context.
Okay, so if the way is the bouncer at the door, RASP runtime application self-protection is like the undercover security guard standing inside the club, watching to see if a patron actually tries to pick the lock on the cash register.
That's brilliant. That is exactly the distinction. RASP does not sit at the network perimeter. It lives inside the application process itself. If it's a Java application, RASP hooks directly into the Java virtual machine. If it's .NET, it hooks the common language runtime. It monitors the actual function calls and data flows occurring in the server's memory in real time.
But wait, I have a major question here. If RASP is sitting inside the application, intercepting and monitoring every single file raid, every database query, every system call, doesn't that just absolutely tank the application's performance? I feel like developers would riot if you introduce that much latency.
It is a totally valid concern, and historically, early in-app security tools did cause performance nightmares, but modern RASP architectures are incredibly optimized. The research indicates the overhead is typically just 2 to 5%, and the reason it's so efficient is that it doesn't have to guess. Because RASP has full runtime context, it doesn't need to run complex regex on every incoming string like a WAF does. It simply waits. It watches the data flow. If a string is passed to a SQL execution function, RASP intercepts the query just before it executes and analyzes the syntax tree. If the user input altered the intended logic of the SQL statement, RASP instantly terminates the execution.
Oh, I see. It doesn't care what the payload looks like. It cares what the payload does.
Exactly. It makes obfuscation useless. It has virtually zero false positives because it only blocks malicious behavior, not just malicious-looking strings. It complements the wave perfectly. The way handles the volumetric noise and known signatures at the door, and RASP catches the sophisticated, obfuscated 0 days that slip past the bouncer.
Okay, that makes perfect sense. Defense in depth. So let's look at the worst-case scenario. What happens if the attacker bypasses the way, evades the RASP, or finds a novel logic flaw that neither control is designed to catch, and they get a foothold? They execute code. They are in. We are now transitioning into the post-exploitation phase. Cloud IAM and lateral movement. The attacker has a beachhead. What is their immediate next move?
The immediate goal is persistence and privilege escalation. They need to ensure they don't lose access if their initial compromised container is rebooted, and they need to expand their reach to find the crown jewels. If they're in a cloud environment, they immediately look at IAM permissions. The research brings up a deeply fascinating white paper by Rhino Security Labs regarding this.
Yes. Rhino Security Labs detailed 21 specific methods to escalate from a low-privilege IAM user to a full administrator in AWS. 21 different paths. And they released an open-source tool, osescalate.py, to programmatically scan for these exact misconfigurations.
Right.
How does this escalation actually work mechanically?
It highlights the extreme complexity of cloud identity policies. It's rarely a direct give me admin exploit. It's about chaining seemingly innocuous permissions. For example, let's look at the IAM.pass role permission. You might give a junior developer an IAM role that restricts them from modifying databases or reading S3 buckets, but you give them permission to spin up EC2 instances and the IAM pass role permission so they can attach service roles to those instances.
Seems reasonable for a developer. They need servers.
Right. But if you don't strictly define which roles they are allowed to pass, the attacker compromises that developer's credentials. The attacker then creates a new EC2 instance and uses IAM pass role to attach the company's main administrator access role to that instance. Then they simply log into the EC2 instance, query the metadata service like we discussed earlier, extract the admin credentials, and boom. They went from a restricted developer to a global cloud admin in 3 steps. Privilege escalation in the cloud is essentially a graph theory problem of connecting permission nodes.
That is terrifyingly logical.
Yeah.
But what if the attacker lands in a traditional on-premise or hybrid Windows Active Directory environment? Because the research notes that attackers actually spend the vast majority of their time in the lateral movement phase, and ironically, it's where they are most vulnerable to detection.
Yes. Lateral movement in a Windows environment is where the attacker is on the clock. Getting in is often quick. Exfiltration is quick. But moving from the compromised receptionist's workstation to the domain controller takes time, and it requires generating noise. One loud step, one tripped alarm, and it's game over. So they have to live off the land.
Living off the land, meaning they don't drop custom malware that an EDR or antivirus would flag. They use the tools that are already there.
Exactly. They weaponize the operating system's native administrative utilities. They rely heavily on tools like Windows Management Instrumentation, WMI. WMI is a built-in framework designed for sysadmins to execute commands remotely across a network. Attackers use it to spawn processes on remote machines without triggering traditional malware alerts. They abuse server message block, SMB for lateral file transfers. They use RDP if they have credentials.
The research also mentioned DCOM and obscure COM objects like mmc20.application. How do those work?
This is highly evasive. The Distributed Component Object Model, or DSOM, allows a process on one machine to instantiate an object on another machine. Attackers discovered they can interact with the mmc20.application.com object, which is tied to the Microsoft Management Console, to execute shell commands on a remote server. To a defender, it doesn't look like an exploit. It looks like the management console is just doing its job. It's like pulling puppet strings from across the network.
So the goal is to hop from machine to machine, dumping credentials from memory, using tools like Mimikatz, until they find an administrator's hash. And then they perform an overpass the hash attack, right?
Precisely. Once they have an admin's NTLM hash, they don't even need to crack the password. They perform an overpass the hash attack where they present the stolen hash to the domain controller and say, here is my cryptographic proof of identity. Give me a Kerberos ticket granting ticket. The domain controller accepts the hash and issues the Kerberos ticket, completely authenticating the attacker as the domain admin.
So if they're using built-in admin tools, native protocols like WMI and DSIFE, and legitimate Kerberos tickets, how do defenders ever catch them? It must look indistinguishable from a sysadmin doing their daily job.
That is the million-dollar question in modern cybersecurity. How do you find the anomaly in the noise? And it's why detection is so incredibly difficult. You cannot rely on perimeter firewalls. You need robust, centralized logging. Specifically, you need a security information and event management platform, often built on the ELK stack, Elasticsearch, Logstash, and Kibana. You have to aggregate event logs from every single endpoint on the network, parse them, and analyze them in real time.
I want to pause here for a second and ask everyone listening to mentally evaluate your own organization's posture right now. Are you actively monitoring intra-network traffic? Are you logging process creation events on individual employee endpoints? Are you capturing PowerShell execution blocks? Or are you just watching the external firewall logs and hoping for the best? Because if you are only watching the perimeter, you are completely blind when lateral movement happens.
I couldn't agree more. If you don't have endpoint visibility, you've already lost. You absolutely need tools like sysmin deployed across your Windows fleet to get granular process-level visibility, knowing exactly which process spawned which child process. And you must have enhanced PowerShell logging enabled. Attackers live in PowerShell. If you aren't logging module loading and script block execution, you have no idea what malicious scripts they are running directly in memory.
Let's get specific on what defenders should look for. The research specifically mentions tracking Windows event IDs. Things like EID 10 for process access, EID 4624 for successful logins, 4648 for explicit credential logins, and 4768 for Kerbero's ticket request. These are the forensic footprints, right?
Spot on. Let's take the overpass the hash attack we just discussed. When an attacker uses a stolen hash to request a Kerbero's ticket, it generates a very specific sequence of events on the domain controller. Specifically, event ID 4768, which is a Kerberos authentication ticket, was requested. By pulling all of these logs into the ELK stack, defenders can write complex correlation rules.
How does the correlation rule distinguish the attacker from the real admin?
By establishing behavioral baselines, the ELK stack evaluates the context. If you see an EID 4768 requesting a ticket for the domain admin account, but the request originates from a receptionist's workstation IP address at 3:00 a.m. on a Sunday, and it is immediately followed by WMI execution commands, which are EID 4624 Type 3 network logons, the SIM correlates those anomalies. It recognizes the behavioral signature of lateral movement and fires a critical alert. It's about connecting the dots.
Which brings us to the absolute worst-case scenario. The incident response playbook. Let's paint the picture. It is 3:00 a.m. The SOC just got that correlated alert from the ELK stack. Lateral movement is confirmed. A domain admin credential was just used to execute commands on a critical database server. The adversary is inside the wire. What is the exact playbook to stop the bleeding without causing a massive outage?
First and foremost, you do not panic. Panic leads to catastrophic mistakes. You do not just start randomly unplugging servers or pulling network cables because you might destroy volatile memory evidence or tip off the attacker, causing them to immediately deploy ransomware as a scorched earth tactic. You follow a rigid, structured framework. The gold standard for this, as detailed in the research, is the NIST Special Publication 800-61, the Computer Security Incident Handling Guide. It prevents chaos by breaking the response down into 4 methodical phases.
Okay, let's walk through them. Phase 1, preparation. But obviously you can't prepare at 3 a.m. This is what you do months before the alert fires, right?
Absolutely. If you are on a bridging call at 3 a.m. trying to figure out who has the executive authority to authorize the isolation of a revenue-generating database, you have already failed the incident. Preparation means having established practice policies. It means having an active incident response team with clear roles. It means deploying the right architecture. The research highlights using platforms like KnowBe4 for continuous user training to prevent the initial phishing vector. But technically, it means having SO platforms, security orchestration, automation, and response like Cortex XOR or swim lane configured and ready.
What exactly does SR do in those first critical minutes?
SO automates the initial triage. When that ELK alert fires at 3 a.m., before the human analyst even rubs the sleep out of their eyes, the SAL platform has already pulled the offending IP addresses, cross-referenced them against global threat intelligence feeds, queried the EDR to see what processes are running on the machine, and packaged all that context into a single actionable ticket. It saves precious minutes of manual data gathering.
All right, phase 2, detection and analysis. The alert is validated. We know it's not a false positive. Now what?
Now the IRT enters the forensic deep dive to determine the true scope of the breach. They use their SIM, like Splunk or ELK, to trace the attacker's path backward. How did they get to the database? Oh, they pivoted from this web server. How did they get to the web server? They pivot into their endpoint detection and response tool, their EDR, like CrowdStrike Falcon or Sentinel. They analyze the process trees. They see exactly what PowerShell commands the attacker executed. They check email gateways like Proofpoint to find the initial malicious payload. The fundamental goal of Phase 2 is to answer one question. Is this isolated to one machine, or are 50 machines compromised? You cannot contain what you haven't scoped.
I think we've all been on those bridging calls, fueled by bad coffee, staring at dashboards, watching systems light up red one by one. It's an incredibly stressful environment. But you have to maintain discipline and know the complete scope before you move to Phase 3, containment, eradication, and recovery.
Exactly. Containment is about stopping the bleeding, but it must be surgical. You use your EDR platform, say CrowdStrike, to issue a network isolation command to the infected endpoints. The EDR drops the host firewall rules, cutting the machine off from the corporate network and the internet, severing the attacker's command and control. But crucially, the machine is still allowed to communicate with the CrowdStrike cloud, so the security team can still interact with it.
This is where proper network segmentation pays massive dividends too, right? If your networks are flattened, containment is nearly impossible.
Huge payoff. If the VLANs are segmented, the attacker can't easily propagate. Once contained, you move to eradication. You use malware remediation tools to scrub the disk. You kill the malicious processes in memory. You delete the scheduled tasks the attacker created for persistence. And most importantly, you execute a global password reset. You reset every compromised credential, revoke AWS API keys, rotate Kerberos tickets.
And recovery. How do we get the business back online?
Carefully. You don't just reboot the machine and hope for the best. The safest path is restoring from immutable backups. Systems like Veeam provide backups that cannot be altered or encrypted by ransomware. You ensure you are restoring to a snapshot taken before the initial compromise occurred, and once the systems are back online, you put them in a penalty box. You monitor them like a hawk with heightened logging to ensure the attacker didn't leave a secondary backdoor that you missed.
Which leads perfectly into the final step. Phase 4, post-incident activities, the lessons learned phase.
This is arguably the most critical phase of the entire lifecycle, and it is the one most often skipped because the team is just utterly exhausted. But you have to do it. You take the disk images and memory dumps and run them through forensic tools like Autopsy to perform a deep, bit-level analysis. You meticulously document the entire timeline in an ITSM tool like ServiceNow or Jira. You have to answer the hard questions. How did they bypass the WF? Why did the RASP fail to block the execution? Why did the ELK correlation rule take 10 minutes to fire instead of 1 minute?
And you perform proactive threat hunting, you assume breach, you assume the adversary is still hiding, and you comb through the network looking for the microscopic shadows they might have left behind. The NIST 861 framework really does just take the panic out of the equation. It provides a scalable, structured, mathematical approach to surviving the worst day of your career.
It does. It forces absolute discipline when everything around you feels like it's falling apart.
Okay, we have covered an immense amount of ground today. We have tracked the modern attacker's journey from the absolute stealth of passive OSINT, exploring the paradox of certificate transparency logs and the mechanics of Google dorking. We moved through the noise of active enumeration, dissecting VOST fuzzing and GraphQL introspection. We broke down the mechanics of server-side request forgery and how RASP intercepts malicious logic in memory. We explored the terrifying reality of cloud IAM privilege escalation and the forensic footprints of Windows lateral movement. And finally, we detailed how the NIST 861 framework gives defenders a structured path to contain the breach. The biggest takeaway for me: defense requires absolute, uncompromising visibility at every single stage of this lifecycle. If you lose sight of your attack surface, the attacker will find the blind spot.
I couldn't agree more. Visibility isn't just a buzzword, it is the fundamental prerequisite for security. If you can't see it, you can't protect it.
Thanks for tuning into InfoSec Bytes. Keep exploring our 200-plus episodes on information security, AI, cloud, quantum, and cybersecurity, incident root cause analysis. Please like, subscribe. We are on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.
Before you go, take a hard look at your perimeter today. If an attacker pulled your certificate transparency logs right now, what forgotten, undocumented subdomain would become their front door?